Hi, I'm Paul Kasabian. I'm a structural engineer. I've taught at MIT and Harvard, and a few years ago at Harvard I talked with one of the TAs about how we should be doing one of those build and test some small structures so that the students can learn about some of the things we've taught in class. And I've never been one of those people who've enjoyed or really thought that it was sensible to do those spaghetti and glue models that you sometimes see people teach kids, mainly because there isn't a structural material that behaves like spaghetti, right? Like, I think if you're really good at doing spaghetti and glue models, that makes you a really good spaghetti and glue model maker, and that's it. So we talked a lot about ways of doing this. We came up with an idea of making it a sort of bridge, essentially a simply supported beam that we would load in front of the class. And we had 3 ways of judging the structures that were designed and built. Way 1 was a general popular vote on the best looking bridge, obviously done at the very beginning. The second prize was for the bridge that could carry the most weight. And the third prize, because we would load the bridges up until they collapsed. And the third prize would be for the bridge that carried the most weight compared to its weight. In other words, material efficiency. So the design looks, the strength of the bridge, and its material efficiency. And the really interesting thing was that it was possible for one bridge to win all 3, or 2, or 1 of the 3 prizes. And the students, there were about 60 graduate architecture students, and I was teaching the structures course that semester, and they got into teams. They made a set of bridges, about 12 or 13, and we tested them all. This video is a video of that day, kind of cut into pieces with me commenting so that you can sort of see my commenting now. It's been a few years since we did it, but I think you'll find it really fascinating. It's really quite exciting, and most of all, you're gonna want to see the bridge at the end. Enjoy. So here we go. This was the classroom that I would teach in, about 60 students. And as you can see, they're having to span from where I'm pointing over to the other side. They're bridges. So bridge number 1. So a few things that I'm going to talk about is as we go through is you can see how this has got a compression flange on the top and tension along the bottom. So that's all good. You'll see that as a general theme for these simple supported beams, essentially. But one of the things that a lot of them sort of missed was sort of how things would work locally, which is why I was asking them to place all their weight in one location. I love seeing this because everyone doesn't know how this is going to work out as it's going to be going along. You can see this sort of this trepidation on whether or not this is going to work. This thing starts to wobble a little bit, so you'll see around this line of it going across, about there's sort of this, is it going to wobble side to side? A lot of them thought about this really. This is a very well thought out structural approach in 2 dimensions, as it were, like viewing it from in elevation, from where these people are sitting. But when you look at it sort of along its length, it's really ends up just being extremely narrow. And they didn't change anything about the end support. So a lot of the thought was put into the main bridge itself, less so at the ends. And here they go. No, I see it moving. So here we got bridge number 3. We've got a much chunkier compression flange up here. So this is looking pretty good. You can see I'm sort of sensitive. And I'm wondering about this because they've supported it really well in the middle, and those tension elements are pretty tight. So what started to occur to me is like, okay, start to load in this zone, because I want them to be able to show what they've thought about. But I also want them to start to load off to the side, to start to see what might happen over here. One of the things I did love was just how you see people over here, just how interested they were in what might be happening. They're all talking to each other. They're trying to figure out what might be happening or not. And again, this is only the kind of discussion and thinking that happens when you see these physical objects behaving under load. Like, people are really learning, and they're willing each other to do well. They put a lot of effort into building these and designing them in the first place. 50, 80, 90,
130. Oh my gosh! Oh. So doing super well, but then, like one of the others, just flipping along its longitudinal axis. You know, that sort of everything fails at its weakest point, and that sort of twisting, torsional, longitudinal twisting stability was one. So this one's really interesting. A lot of different bits of material look structural, right? Like we've got pieces that are going up as a compression, pieces here for tension. They've got it deeper in the middle. Very exciting. Very lots of connections. The thing is, it's so floppy, right? And a lot of that's got to do with the fact that there isn't continuity. Like the continuity in this flange going up and down is trying to go through these very slender elements, and the same down here on the bottom. So a lot of good ideas. The whole point, I think at the end of the day, everyone just wants to know when is it going to collapse and how. I think this one surprised people because they realized how quickly how flexible it was. I was threatening to cut a few of the cables. Ah! Oh my gosh! Oh dear. Funny how the more pieces there are, the more it starts to collapse. Okay. So, very similar to one of the earlier ones, a sort of underslung truss, chunky compression flange, cables going along the bottom, more regular pieces coming down. That's good in terms of providing regular support and motion for where the weights might go, stabilizing the compression flange, that's good. There's nothing really going between these guys here that helps stabilize them from flopping around, but, you know, let's just see how it plays out. Okay, it's pretty chunky. Oh, nope, did you see it wobble a little bit? Side to side? Yeah, keep an eye down here. That's where it's starting to most be visible, but that movement down here is really because it's rotating about this axis at the ends. This is the most weight so far. You can feel it wobbling. He's trying to balance the weight. Oh my god, there he goes. Yep. You could sense it as he was placing, right? So at this stage, some other class actually had to come in because we ran long. And so we moved, I think we had three more that we did outside, which is 11, 12, and 13. So we did these outside. And so this one is clearly inspired by, let's say, the Alamillo Bridge in Seville by Santiago Calatrava. He did it for the 1992 Expo. Baseline is a cable-stayed bridge, inclined mast tower, thickened base, and cables coming down. Very much a dramatic sculptural structure. And so there's, essentially they're using something that they know works. But you'll also notice that some of these cables are not super tensioned up. Again, it's very difficult to tension cables. And the more you have, if you start to tension some of the other ones become slack. It can be a tricky thing. However, they did do a really good job at doing a rigid base and having a sort of proportioned backspan, using not really the weight of this tower, which is what the Seville project does, but using the rigidity of its connection to the base. We're really adding some significant weight to this. It's doing very well. At this point, I think we'd started to load almost as much as any of the bridges have done. You might start to see it twisting a bit. He's trying to load it to sort of rebalance. Oh dear. But that was a good chunk of weight. And by now, this is, as you can tell, one of the main lessons, overall stability. Bridge number 12 of 13. So this is going very much for very chunky towers at either end. See one here, and then one over at the other end over here. And a whole series of cables. And then on top of that, they did an underslung truss to the midspan, which a little bit too much, as it were, you might say, but good thinking in that the cables that reach out to the middle span being the most shallow are the least used, as it were, and the least efficient. But you'll also see just how floppy some of these are as well. I don't know if they added this as an afterthought, but good job with the sort of chunky towers to take the load up to. A little bit, you can see this is layered construction, and there's already with this weight a little bit of an open. Oh my gosh! Oh dear, oh dear. I think that happened sooner than we thought it would. But you can see it's locally failed, not because of the system, so much as their overlapping of their materials produced a local weak spot. So although they had the depth that might have worked for them, their connection detail, their sort of lap detail didn't work. Oh dear. Okay, we are on to bridge 13 of 13. Lucky number 13. Let's see how this one does. So they're making sure it's, good job. Making sure that the end supports are in place properly and they're stable. That's going to matter, right? Okay. So the reason we thought this would do quite well was a number of reasons. It's obviously a good system, chunky top, compression flange, and correctly shaped, thicker in the base, thicker in the middle, rather, tension cables along the bottom. They had multiple cables, they were well strung, they were stable at the end, they put a bunch of effort, this is the cable coming through, to making sure that this wouldn't pull through. And so as we looked at this early on, and I was discussing this with the TAs, and Andrew in particular, that we're like, I wonder how this one's going to fail. Because a lot of the other ones had an obvious weak point, right? They had a place where we're like, at some point this is going to pull earlier than the rest of the structure. The sort of weak link in the chain concept. And here we thought they'd managed to address all the different things that we're normally looking for really well. So we went, okay, either way we know this is going to carry quite a bit of load. Let's leave it till the end. And there we go. It's well-deserved applause, because now we're looking for the fact that we have no more weights. That is literally it. We didn't think any bridge could carry that. And Andrew's now pointing out a little crack that started just there in the mid-span. They're testing, the cables are doing pretty well. Who says, has anyone else got any weight? Now just listen carefully though. I hear it. Okay. Oh, there was another one. Oh, another crack. Move out the way. And oh God, there we go! Wow, it all failed. That was amazing.